Okay, so we define conweb as a constant working process, and this is a protocol under which a new job is introduced to the line each time a job departs. So what this means is we will try to get a constant web from the inside of the manufacturing line, meaning that from the beginning to the end, independently of how many stations we have, we want to keep this constant width. Okay, and we're just going to add a new part or a new entity to this line when an entity departs that last station of the manufacturing process. Okay, so that's how we are going to keep this constant width. And this type of protocol assumes two things. The first one is that the production line consists of a single routing along which all parts flow. So every single part will go to this station, this station, this station, and this station. There's not going to be any deviation from that sequence. And that the jobs are identical so that the width can be measured in units. Okay, so all units are identical. You are processing the same type of component, the same type of part, and they are going through all the stations in the manufacturing line. Okay, so the way this works is once we have processed that part on the last station, that departing job is going to send a card back to the beginning of the line to authorize the new or the release of a new job. Okay, so we start the process one more time. One entity leaves the system, one enters the system. We also compare the three protocols that we described in this lecture on the next slide. So if the facility contains multiple routings that share workstation, or if different jobs require substantial different amount of processing on the machines, then the things are not so simple, meaning that the strategies that we are discussing are based on the assumptions that I described on the previous slide. On this particular figure here, what we are doing is just comparing the three protocols, the conweb, the pure push, and the pure pull. Remember that push is based on MRP and pull is based on the Kanban system. And again, the idea is to see how these three protocols are different. So again, the conweb will allow entering a new job when a job departs the system. So you're going to send a signal back to the beginning of the line to introduce a new job to the manufacturing line. A pure push will basically push as many jobs or entities as possible. So you're going to be sending those through all the stations in this way without taking into consideration the actual width of the system. And then the final one is the pure pull Kanban system. And in here, as we discussed last time, you are going to be sending these signals to the previous stations in the line when jobs are required to be completed. So you are going to be producing entities or new parts as long as there's a request from the next station on the line. Okay, so in that way you will keep your web at the minimum. Okay, so far we have described different formulas and theory to analyze push systems. Okay, and that's what we have done at the beginning of the semester. But now we want to have some type of strategy to compare these push systems to or with conweb lines. Okay, and that's where this mean value analysis model come into play. Okay, so to analyze convex lines and make comparisons with push systems, it is useful to have a quantitative model of closed convex systems. So this is similar to Kinsman's equation model we developed for open push systems in the variability basics lecture. And the notation that we are going to use to describe an end station convex line is the one that is listed here. So we're going to have UW, UJ of W, where W is the width level. So remember, in convex lines, now we want to focus on keeping the same width level across the manufacturing line. So that's going to be one of our performance measurements. So we're going to keep that width level to a certain number. And the utilization of the station is going to be UJ. CTJ is for the cycle time at a particular station J with a specific width level. CT without the J index is the cycle time for the line. So that includes all the stations. THW is the throughput of convex line with the width level. And then WIPJ or width J is the average width level at a particular station when you're trying to keep your level at a particular width number. Okay, so those are the 5 components or notation for this mean value analysis model. Okay, so this is going to be, this mean analysis model is an iterative process. Okay, so we're going to start by letting WIPJ equal 0. For a width level of 0, and the same thing for the throughput. And the mean value analysis algorithm will compute the cycle times, throughput, and station by station width level as a function of the number of jobs in the convex line in iterative fashion by using the following. Okay, so we're going to start by adding jobs one by one, and then we're going to see how the algorithm is going to perform with that information. So for CTJW, we have that expression 10.1. We can also compute the cycle time for the line with 10.2 or formula 10.2, which is the summation of all the cycle times for all the stations. And we can get the throughput as the width divided by the cycle time at a certain level of width, and then get the width for each one of the stations by multiplying the throughput on the cycle time for that particular station. These formulas are going to be kind of difficult, or this algorithm is kind of difficult to implement by hand because you're going to be doing a lot of computation manually. So it is a good idea to try to do this in a spreadsheet. Can be used to generate curves for the throughput, the cycle time for convex lines. Other than that, the best, worst and practical worst cases. So to illustrate the use of these formulas, we're gonna work this example, and we're gonna refer back to the PennyFab example that we discussed at the beginning of this course. So remember, we have 4 stations, and each station take an average processing time of 2 hours. And then we're going to consider the PennyFab with reduced variability. So we're going to say that CEJ is going to be 0.5 for each one of the stations. And we're going to start with a width of 0 and a throughput of 0 equals 0. And from there, we can compute the following. So if we can compute the cycle time J of a width level of 1, and that is going to be using this formula right here, 10.1. So that's going to be equal to TE square of J divided by 2 times CE square of J minus 1 times the throughput of 0 plus the width J of 0 plus 1 times TE of J Okay, so from here we know that this is going to be equal to 0, right? And WIPJ of 0, which is here, is going to be equal to 0 as well. So at the end, what we have is that the time for each station is going to be equal to 2. Okay, which kind of makes sense, right? You only have one job. That's what's going to take each job to be processed. So 0 here, you multiply all this by 0, it's going to be 0. This is 0 plus 1, so 1 times TE of j is going to be equal to the value that we was given for the problem. Okay, so that confirms our initial assumption. So from here, for j equals 1 up to 4, since all stations are identical, CT of this width level is going to be equal to 4 times CTJ of W, and therefore CT of 1 is going to be equal to 8 hours. Okay, so we know that when we have a width level of 1 and the time that it's going to take a part to be processed is 2 hours, and we know all the stations are identical, so if we only have one part being processed, the time it's going to take for that part to go through the system is going to be the time that she's going to spend on each station, which is 2 hours, and the summation of 4 stations is going to be equal to 8. Okay, so that's what we're saying here. And we can also compute the throughput. So throughput is TH of 1 is going to be 1 over CT of 1. So is 1 over 8 for this case. Okay, so we got the CTW, J. With that, we can compute the CT, or the cycle time for the whole manufacturing line. We compute the throughput, and now we want to compute the WIP for each one of the stations. So the average WIP at each station is going to be WIPJ of 1, which is going to be equal to the throughput of 1 times the cycle time J of 1, and that's going to be equal to 1/8 times 2, which is going to be equal to 1/4. Okay, so that's assuming that we have a WIP level, or a constant WIP level of 1 through our manufacturing line. So now we are going to repeat the process for a constant WIP of 2. Okay, so for W equal to, we can compute CTJ of 2, which is going to be equal to TE squared of J divided by 2 times CE squared of J minus 1 times the throughput of 1 plus WIPJ of 1 plus 1 times TE of J. Okay, so we know the value of TE. TE squared is going to be 2 squared divided by 2 times 0.5 squared minus 1 times the throughput of 1. So what would be that value? So it's going to be this value right here, 1/8. Okay, so you see now the iterative nature of this method. So you're going to be referring back to the values from the previous WIP. So it's going to be 1/8 plus, yes, 1/4 plus 1 times 2. And this is going to be equal to 2.313. So by adding an additional unit to the WIP, we are increasing our cycle time at each one of the stations. Okay, which kind of makes sense. Okay, so the cycle time for the line at 2 is going to be equal to 4 times the cycle time J of 2 which in this case is 4 times 2.313, and this is 9.225. And the throughput of 2 is going to be equal to W divided by the cycle time of 2. So in this case, it's 2 divided by the cycle time of 2, which is 9.25. So this should be equal to 0.216. And if we continue, we can also compute the WIPJ for each one of the stations. So if we move to the next slide, you will see all the computations for all the W's up to 12. Okay, so by adding an extra unit of width, you see how the throughput of the line increases. The cycle time also increases. So that's the cycle time, and the cycle time for each one of the stations will also increase, as well as the width level at each one of the stations. So for example, in this last one right here, you know that the width level at the line is 12. That kind of makes sense, right? Because that means that in each one of the stations, you will have 3 units waiting. So 4 stations times 3 equals 12. Okay? So using the same procedure, we can also generate the throughput and the cycle time for the case in which we increase the capacity. For instance, by reducing the average process time at stations 1 and 2 from 2 hours to 1 hour. So once you generate this spreadsheet, which what I recommend to do with this type of problems, you can start playing with those numbers, and that should allow you to see the performance of the manufacturing line when you introduce these new performance measurements and these new inputs. So we have done this. On the next slide, I have the plot of the results for both the reduced variability case from table 10.1, which is this one, and increased capacity case, along with the best, worst, and practical worst cases. And this is a plot that is coming from your textbook. So here we can show we have the width and the throughput. So how the width impacts the throughput, and how the best case, the practical worst case, and the reduced variability match that particular graph. And you can see how increasing the capacity also improves when compared with the reduced variability case. Notice that both cases represent improvement over the practical worst case. Okay, so the practical worst case is here, and by reducing the variability and increasing the capacity, you become a little bit closer to the best case scenario. Since they enable the line to generate greater throughput for a given width level. So these are the things that we have been discussing over and over again. So in order to you to make an improvement to your line, you should always check to reduce the variability of your system. That should be the less expensive way to do it. Obviously, if you increase capacity, there's going to be an additional cost. So maybe adding a machine, or maybe adding another person to help you with the manufacturing process. So in this example, speeding up 2 of the stations produce a greater improvement by reducing the variability on all stations. Now that we have models of both push and pull systems, we can make some comparisons to deepen our understanding of the potential benefits of pull systems. We can begin this comparison by comparing the Conweb versus the MRP. The MRP again is the typical system, and then we contrast the Conweb with the pure pull system, which is the Kanban system. Okay, so one thing that I want you to have very clear, here we're focusing on this Conweb protocol, but you need to understand that this is not applicable to all systems. Okay, so keep that in mind. There's some assumptions. That's why you would always, so you can think about, well, if this is better than push system, why you will see mostly push systems in manufacturing process. The reason is this type of protocol will assume these two main things, and if your system is not following those specific things, then this might not be the best protocol to use. And obviously, most of the people are familiar with typical push systems, and that's what you will see mostly in manufacturing processes. So if you have enough space for saving, or not for saving, but for storing items, and you know that you have a very steady demand for those items, maybe an MRP system or push system works well for you. Okay, but the idea here is thinking about the benefits of the other two protocols. We discussed how the pull system allows you to decrease the number of defects or increase your quality. So there's some added benefits into these other two protocols that you should be able to consider. So let's focus on a general description of what are the comparisons of Conweb with these push systems. And defining here what an MRP system is, in case you have not heard about this concept before. MRP stands for Materials Requirement Planning, or a production planning, scheduling, and inventory control system used to manage manufacturing process. So the idea here is you look at the forecast, you see your demand based on your history, and you forecast what's going to happen in the future, and you plan for that forecast. So I'm forecasting to have these many units sold, or to be selling these many units. So I'm going to be basing my production schedule based on that forecast, and I'm going to push that many units into the system, so I should have that many units available for selling if that demand occurs. Okay. Okay, so a fundamental distinction between push and pull systems is the following. Push systems control throughput and observe width. So again, you are going to be focusing on producing this many units in this time. Pull systems control width and observe the throughput. So by controlling the width, I'm basically saying how many units I can produce. So for example, in MRP systems, we establish a master production schedule, which is what I was referring to when you look at the forecast, which determines plant orders release. This in turn determines what is released into the system, and depending on what happens in the line, however, the width level may float up and down over time. So we are not focusing on keeping that width level steady. We want to be able to satisfy that final goal of producing a certain number of items. In a pull system, the width level is directly controlled by setting the cart counts. So you're going to be seeing a specific number of units waiting, or being moved or transferred from station to station. However, depending on what happens in the line, the output rate may vary over time. So we talk about the case in which if you have unexpected failures in one of the stations, then by not having enough WIP into your system, then your production schedule might be affected. Okay, so which approach is better? While this is not a simple question, we can make some observations. In terms of observability, WIP is directly observable while throughput is not. So hence, setting WIP as the control in a pull system is comparatively simple. We can physically count jobs on the job floor and maintain compliance with the cap or the WIP cap. In contrast, setting the release rate in a push system must be done with respect to the capacity that you have in your system. So in terms of observability, since WIP is robust and observable, while throughput is sensitive and can be controlled only relative to the observable parameter of capacity, this is a powerful argument in favor of a pull system or a pull production system. So we can observe what the WIP is and based on that control our manufacturing process while focusing just on the final goal and setting up the capacity to achieve that goal might not be as easier to control. In terms of efficiency, a second argument in favor of pull systems is that they are more efficient than push systems. And by more efficient, we mean that the WIP level required to achieve a given throughput is lower in a pull system than in a push system. So here we have the law of con-WIP efficiency. So that basically states that for a given level of throughput, a push system will have more WIP on average than an equivalent WIP system. And that is kind of logical, right? Because all the focus of the con-WIP protocol is to keep the WIP constant. So so you would expect to have a higher WIP on a push system. For a given level of throughput, a push system will have longer average cycle times than an equivalent con-WIP system. Okay, so that's the other important thing in terms of comparing these two systems. But again, you just want to keep in mind that these con-WIP systems or protocols are targeting a very narrow area of all the manufacturing processes that you can have. And most of the time, you will have manufacturing processes in which you are going to produce multiple type of products, different families. So one of the assumptions that a con-WIP system makes is that all the products will go through the same stations. And in today's manufacturing system, that might not be the case, certainly. So we made those 2 points in terms of push system versus pull systems. Now I want to compare the con-WIP with the Kanban system. And the Kanban is the scheduling system for lean manufacturing and just-in-time manufacturing. And the Kanban system basically is the one that uses the cards to send the request to the stations that are before in your process. And we observed that in the video. So let's compare these two, con-WIP versus Kanban. So both systems will establish a WIP cap, and that's the idea behind both of these. Remember, the just-in-time or the pull pure pull system would go and check and make a request to the previous station, and then check what the status is, and then you make a request to the previous station. The difference between the pull system and the CONWEB is that in the CONWEB you will go up to the first station in the line. Okay? So both systems will establish a web cap that exhibits similar performance advantages relative to MRP. Specifically, both CONWEB and Kanban will achieve a target throughput level with less weight than a pure push system and will exhibit less cycle time variability. Okay, so in terms of these particular 2 points, both of them provide the same benefits, CONWEB and Kanban. However, there's some card count issues in the just-in-time or Kanban system. The most obvious difference is that Kanban requires setting more parameters than does CONWEB. And in the CONWEB system, you will only focus on the end of the line and the beginning of the line. However, in the Kanban system, you have to keep control of all the stations in your system. So CONWEB system, there's only a single card count to set. Since coming up with an appropriate count requires a combination of analysis and continual adjustment, this fact means that CONWEB is easier to control in that sense. In terms of product mix issues, the experts on Kanban were clearly aware that it would not work in all production environments. Okay, so that's what we have been repeating in the last few minutes. That's the same thing for CONWEB. So what is in CONWEB, while still requiring a relatively steady volume, it's much more robust to swings in product mix as a result of the planning capacity used by the process of generating a release slip. Okay, so these are, again, very general description of these two systems. The focus for this lecture in particular is that you become familiar with the CONWEB protocol. We are assuming that you have some type of knowledge of production systems. We have been discussing a lot about push systems. We have not touched into the pull systems a lot, but the idea here is that you get familiarized with these concepts in class. So that basically concludes this lecture. I want to, let me see, stop here, and before we transition